There's a label on almost every industrial scissor lift you'll ever use. It reads ANSI MH29.1 compliant. Most operators walk past it every single day. But here's the question that actually matters. What does that label mean in the real world? Not in a laboratory, not in a testing report. On the floor, on your shift, today. This video is about building that knowledge. By the end, you'll be able to look at any scissor lift and know, not assume, whether it meets the standard. You'll know what good looks like, what a red flag looks like, and exactly what to do when you can't tell the difference.
Take a look at this diagram. At first glance, a scissor lift seems simple. 2 crossed frames, a platform, some hydraulics. But internally, a scissor lift is a concentration of high-energy mechanical forces. A single off-center load generates forces that multiply through every arm, every pivot, every weld. One weld failure doesn't degrade performance. It triggers catastrophic collapse.
Here's a lift you'd recognize from any warehouse floor. Blue frame, guardrails, platform. Looks straightforward. But the diagram on the right shows what's actually happening inside. A hydraulic cylinder under extreme pressure. Pivot points where stress concentrates. Weld joints that are potential failure points. The manufacturer made those engineering decisions before this machine ever reached your facility. Your job is to verify that those decisions are still intact. Let's get grounded in the standard. ANSI MH29.1 covers all industrial scissor lifts, hydraulic, pneumatic, or mechanical. And regardless of power source, every lift has 4 structural systems you need to understand. The platform assembly, the horizontal load surface you work on. The pantograph legs, the articulated support mechanism. The actuation system, the energy source and control valves. The base frame, the foundation everything sits on. All 4 have specific requirements, and all 4 leave observable evidence when they're working and when they're not. Here's something most people get wrong. A compliance sticker tells you that a machine passed testing on a specific date. It tells you nothing about what has happened since. Real compliance has 3 visible dimensions: documentation, nameplates and manuals that must match the hardware. Hardware, physical components that leave visible evidence of correct engineering. Behavior, how the machine actually operates. A sticker proves past testing. Observation proves current safety. Every shift, you are the measurement instrument. Safety is never one person's job. The standard defines a shared compliance ecosystem, 2 sides that must both hold up. The manufacturer's side, provide a safe design, publish accurate load ratings, supply complete operator manuals. If any of those are missing or wrong, compliance starts broken. The operator's side, daily inspections, respect every load limit, and keep the equipment unmodified. The moment someone welds a bracket onto a platform or bypasses a switch, the manufacturer's safety testing is voided. The machine becomes an unknown. One of the most dangerous real-world scenarios on a scissor lift? Edge loading. This is what happens when a heavy wheeled load is rolled onto the edge of the platform. Gravity creates a stress multiplier effect. The further a load is from the machine's center, the more tipping force is generated. It doesn't take much to exceed what the structure can handle. MH29.1 addresses this with a demanding test. Manufacturers must apply 125% of rated load at the furthest point on the platform, not at the center, at the edge. What this means for you: every scissor lift has a separate edge load rating, lower than its overall capacity. You need to know that number before you roll anything onto the platform from the side. Here's something that surprises most operators.
A small amount of platform flex under load is not a defect. It's calculated physics. On an 8x5-foot platform, the maximum allowable deflection is 0.78 inches under full load, less than an inch, and it's intentional. The structure is designed to flex slightly rather than resist rigidly and fracture. The issue is not deflection. It's what happens after. When you load a platform and walk away, it should hold its height. Any drop is called vertical creep, and vertical creep is a red flag. Let's go deeper on vertical creep. The hazard is internal. Leaking valves or failing cylinders allow hydraulic pressure to bleed off slowly. The platform doesn't drop suddenly, it drifts. The rule? Vertical creep must not exceed 0.5% of maximum travel, measured over 15 minutes under full rated load. That is an extremely tight tolerance. The field test is simple. Load the platform, raise it, set a timer, and watch. If it moves, it fails. The scissor mechanism has a physical limit to how far it can extend. Exceed that limit, and cylinders overstroke, welds fracture, and the entire pantograph assembly can fail. The standard requires physical stops, not just electronic sensors. Electronic limit switches tell the system where the platform is. Physical stops prevent structural destruction if the electronics fail. Both must be present. Both must be functional. During your walk-around, look for them. They should be visible, intact, and not painted over. Now, let's bring it together. This is the anatomy of a compliant lift, and every labeled feature has a specific requirement behind it. Point A, precision hydraulics. No creep. Check valves installed and sealed. Point B, structural limit stops. No overtravel. Physical barriers in place. Point C, 11-gauge steel bevel guards. No crushing. Point D, rated base and leg foundation. No tip-overs. Remove any one of these features, and you haven't degraded performance. You've introduced a specific, documented failure mode. Here's your practical walk-around map. 4 checkpoints, each visible without any tools, each under 2 minutes total. Point 1, platform edges. Check that edge load ratings are marked and no loads are staged at the perimeter. Point 2, base guards. Rigid steel beveled guards, not rubber skirts or accordion curtains. Point 3, push button controls. Test the spring back on each button before the shift. Point 4, nameplates. Present, legible, and matching the operator manual. The nameplate is the machine's operating contract. It is the physical record of what this specific lift was engineered and tested to do. And it must do 2 things: exist and match. A compliant nameplate states the overall rated capacity, and separately, the end edge load limit and the side edge load limit. Those numbers are not the same, and every operator needs to understand the difference. A missing plate, a painted over plate, numbers that don't match the manual, any of those conditions means you cannot know the safe operating limits of that machine. And if you can't know the limits, you cannot operate it safely. The control station is where your intent meets the machine's action. MH29.1 has a specific requirement for how that interaction must work, and the reason is purely about emergencies. Press the button, the lift moves. Release the button, the lift stops immediately. The button springs back to neutral on its own. Why? Because in an emergency, muscle memory takes over. People release pressure when startled.
This design turns the natural startle reflex into an automatic safety response. A sticky button neutralizes that reflex. The operator loses their emergency stop. This is one of the most dangerous misconceptions about scissor lift safety. That yellow accordion skirt around the base, most people assume it provides foot protection. It does not. Accordion skirts are debris barriers. They keep loose material out of the mechanism. They provide zero physical protection against crushing. The MH29.1 requirement is a beveled toe guard, rigid 11-gauge steel at least 8 inches wide, slanted 30 degrees inward. That bevel redirects a foot outward. The skirt does not. Here's your field reference. 2 columns, what compliant looks like and what demands immediate action. Compliant machines have permanent legible safety labeling, operational mechanical limit stops, functional landing interlocks. Red flags are missing, painted over, or torn data plates, defeated safety devices like bypassed switches, unexplained hydraulic drift, or a spongy control response. Any single red flag is sufficient reason to tag the machine out of service. You do not need multiple problems. You do not need confirmation. One red flag, tag out, report. This matrix maps each major component to what good looks like and to the specific safety failure that a red flag represents. Nameplate. Good means it matches the manual. A missing plate means unknown load limits. Controls. Good means they spring to neutral. Sticky buttons mean you cannot stop in an emergency. Base. Good means rigid 11-gauge steel. A flexible skirt is a severe pinch hazard. Platform. Good means it holds static height. Excessive sagging means hydraulic integrity is failing. Small observable clues are windows into larger hidden risks. That's the core skill. Before a lift reaches your floor, it's already gone through a 3-stage verification process. Understanding this helps you interpret what you find during inspection. Stage 1. Design documentation. Engineering calculations and material specifications. This is where compliance is born. Stage 2. Internal checks. Manufacturing quality control and weld inspections. This is where compliance is built. Stage 3. Functional evaluation. Factory baseline testing. This is where compliance is confirmed. Those 3 stages happen before the machine leaves the building. Your daily inspection is stage 4, the ongoing field verification that the factory results are still intact. 4 questions, less than 2 minutes. The difference between assuming a machine is safe and knowing it is. 1. Does the physical nameplate perfectly match the manual? 2. Do the push buttons instantly spring back to neutral? 3. Is the toe guard rigid steel or flexible vinyl? 4. Does the platform hold its height or does it visibly creep? If the answers aren't clear, stop operation. Tag out. Report it. Not after the shift. Now. The final mindset shift: stop thinking like someone using a lift. Start thinking like someone inspecting one. At pickup, can you show me the MH29.1 compliance documentation? Not as a formality, as a genuine requirement. On site, has the hydraulic system been drift tested? If no one knows, run the 15-minute observation yourself before you commit to the work. Before every load transfer, does this task exceed the edge load rating? Not the overall capacity, the edge load rating. Those are different numbers.
Here's where we land. Safety is an active, ongoing system,
not a certification event. You do not need a lab to verify observable safety. Spotting red flags prevents catastrophic failures. Informed operators elevate safety standards across the entire industry. The engineering has been done. The safety is built into the hardware. Your role is verification, confirming that what was proven in the lab is still true on your floor today. Trust the engineering. Verify the evidence.